Before electronic systems existed, mathematical work that required thousands of operations was completed by hand. Large tables of logarithms, trigonometric values, and astronomical data were produced by people sitting in rows, performing arithmetic according to written instructions. These workers were called computers. The term referred not to a machine, but to a person whose occupation was calculation. Governments needed trajectory tables for artillery. Shipping companies needed celestial navigation data. Insurance firms needed actuarial projections. Engineering projects required stress analysis and load distribution across structural members. No machine could perform this work at the required scale. The calculations were divided into steps simple enough to be repeated without error. One person would add, another would multiply, a third would check. The results were recorded in ledgers and transferred to the next stage. Rooms were organized like production floors. Silence was maintained. Accuracy was absolute. The work was slow, but it was systematic. It continued decade after decade because there was no alternative. The tools were simple. Paper ruled into columns, printed logarithm tables that reduced multiplication to addition, slide rules for approximation, mechanical adding machines that required a hand crank for each operation. Some institutions used difference engines, devices built from gears and levers that could evaluate polynomial functions, but these were rare and limited in scope. Most work was done with a pencil, a printed reference, and a method. Methods were distributed as procedural documents. A single equation might be broken into 50 steps. Each step was written in plain language. Step 1, locate the sine of the given angle in Table 4. Step 2, multiply the result by the constant provided in column 6. Step 3, subtract the value obtained in the previous row. Every instruction was literal. There was no interpretation. The computers did not need to understand the purpose of the formula. They needed to execute the sequence without deviation. Supervisors verified the procedures and checked the output.
The work was subdivided by operation. One group handled addition, another handled subtraction. Multiplication was broken into smaller additions when necessary. Each person completed the same task hundreds of times per day. A single ballistic table might require 30,000 calculations. One error would propagate through every line that followed. For this reason, every result was computed twice by different people using the same method. If the two results disagreed, both were discarded and the work was repeated. A third computer, working independently, would then verify the matched results. This created redundancy at every level. 3 layers of labor for one line of output. The cost in time was accepted because the cost of inaccuracy was greater. The system depended on the assumption that errors were random, not systematic. If the method itself was flawed, all 3 computers would produce the same wrong answer. Supervisors checked not only results, but procedures. Audits were frequent. Silence reduced distraction. Consistency reduced error.
Accuracy was enforced through repetition and comparison. A single miscalculation in a navigation table could place a ship miles off course. A single error in an artillery table could mean rounds falling short or long. The work was not approximate. It was exact within the limits of the tables and methods available. Computers were trained to recognize common errors: a carried digit forgotten, a sign reversed, a decimal misplaced. Each mistake had a pattern. Supervisors learned to spot them. When an error was found, the entire sequence was redone from the beginning. No partial corrections were allowed. Some calculations took weeks to complete. If an error appeared in the final stages, the weeks were lost. The system had no shortcuts. There was no way to recover time once spent. This created pressure, but the pressure was quiet. The work continued at the same pace regardless. Speed was never prioritized over correctness. A table delivered late was acceptable. A table delivered wrong was not. Institutions could not function without this work. The military required firing tables that accounted for air resistance, wind, and the rotation of the Earth. Astronomical observatories required ephemerides that predicted the position of celestial objects years in advance. Engineers designing bridges needed to distribute load across hundreds of members, each requiring separate force calculations. Telephone companies needed switching tables. Insurance companies needed mortality tables. Census bureaus needed population projections. All of this required arithmetic at a scale that exceeded what any individual could perform. The computation rooms provided it. They were not peripheral, they were central. The results they produced became the foundation of other systems. Navigation charts were printed from their tables. Guns were calibrated using their data. Buildings stood because their figures were correct. The labor was invisible to the systems it supported. The tables were published without the names of those who computed them. The work was tiring in ways that were not immediately apparent. Sitting for hours without variation, eyes fixed on columns of numbers, hands writing the same figures in the same sequence, mistakes born not from ignorance but from fatigue. A moment of inattention could undo a day's work. There was no physical exertion, but there was no rest either. The mind could not wander. Calculation required continuous focus. Some institutions imposed quotas, a certain number of lines per day, a certain accuracy threshold. Workers who fell behind were replaced. Workers who made too many errors were dismissed. The rooms were staffed year-round. There were no seasonal slowdowns. The demand for tables was constant. Expansion was limited by the number of people who could be trained and trusted. As the need for calculation grew, the rooms grew larger. But there was a ceiling. Human labor could only scale so far. The bottleneck was not method, it was capacity. Electronic computation appeared without warning in most institutions. The first machines were large and expensive, installed in military or university settings. They performed in hours what had taken months. The methods used by human computers were translated into machine instructions. The same procedures, the same checks, but executed at a speed that made human labor obsolete. The rooms were not emptied all at once. Some institutions continued manual work for years, either because they could not afford machines or because they did not trust them. But the direction was clear. One by one, the calculation rooms were repurposed. Desks were removed, ledgers were archived. Computers, the humankind, were reassigned to clerical roles or let go entirely. There were no ceremonies. The work simply stopped. The systems that had depended on them continued without interruption. The tables were now produced faster, in greater volume, with fewer errors. The need had not changed. The method had. Records of the work remain in institutional archives. Ledgers filled with handwritten figures, procedural manuals explaining the division of labor, photographs of rooms filled with desks, each desk occupied by someone holding a pencil. The photographs are undated. The faces are unnamed. What remains is evidence of duration, years of arithmetic, compressed into volumes that no one opens. Some of the tables are still in use, reprinted from the original computations. The numbers are unchanged. The method by which they were obtained is forgotten. A few institutions kept their calculation rooms intact for a time, as if uncertain whether the machines would last. The rooms were eventually cleared. The tables were transferred to magnetic tape, then to disk, then to formats that required no physical storage at all. The continuity is unbroken. The calculations continue. The labor that produced them has been replaced entirely, and the replacement is irreversible.